Welcome to PowerPoint Chapter 7a. Chapter 7 is so complex. Once again, we've divided it into two PowerPoints, 7a and 7b. This one is all about atmospheric motions. That's the title of the chapter. Basically, what makes the wind blow and why the wind blows. Eventually, we'll be covering all kinds of things, including global circulation, high pressure and low pressure systems, and so on and so forth. This chapter is going to cover horizontal pressure changes in wind, surface and upper level weather charts and how the wind is depicted on them, why the wind blows and how the wind blows, winds down here on the surface where we live, the influence of extreme winds, and some of the windiest places in the world. Now the figure at right there is a dramatic picture. It's the cover picture from your Chapter 7 book, which shows waves caused by the wind crashing up against the shores of the Great Lakes. Quite amazing picture. All right, so here we go. Ultimately, the wind blows, the air on the surface of the earth moves because of horizontal differences in pressure. If the pressure is higher in Monterey than it is in Fresno, the wind is going to come from that direction. If the pressure is higher in Reno than it is in San Francisco, the wind is going to come from where the pressure is higher. It takes a shorter column of dense cold air to exert the same pressure as a taller column of less dense warm air. Warm air aloft is normally associated with high pressure, and cold air aloft is normally associated with low pressure. This is aloft above your head. Down here at the surface, it is horizontal differences in temperature that produce horizontal differences in pressure, which ultimately results in the air moving around, which we call commonly the wind. Okay, I got to tell you a little story here. Back in the days when I was in television, back in the 90s doing TV on weather on Channel 24, I worked with an anchorman. He's still working there now, Bud Elliott, and an anchorwoman, Steph Barugian. It was a particularly windy, cold night in the wintertime. And, so that they would kind of know what I'm going to talk about when I get on the air. They wanted to know why the wind was blowing so strong. And I explained to them, well, there's a very strong high pressure off the northwest California coast. The pressure in Crescent City, California is higher than it is in Yuma, Arizona, blah, 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 blah. And my friend Bud Elliott just cut to the chase. And he said, Sean, it's very simple. Why don't you just tell our viewers that San Francisco blows, LA sucks, and we're in between? Well, I couldn't exactly say that on TV, but meteorologically, he was correct, and he really cut to the chase and explained it in very simple terms. All right, so we start with two columns of air, equal with respect to how many molecules they contain. They each have the same pressure, and they each have the same temperature. So let's say we decide to heat up the column of air in City 2. Same number of molecules, but because those molecules are excited by being heated, they occupy more space, and the warm air starts to rise. And if this process continues, what you end up with is a piling up of molecules aloft with column 2, City 2, which means you have high pressure aloft with warm air. Consequently, you also have low pressure aloft associated with cold air in City 1. So temperature has everything to do with the density and the pressure of the air. And what you end up creating here is a little circulation. If you have high pressure aloft in column 2, that means you have lower pressure on the surface. If you have low pressure aloft in column 1, that means you have high pressure on the surface, and you get a circulation. As air piles up aloft, warmer air, surface pressure decreases. If low pressure aloft is nearby, i.e. cold air aloft, then the air in that column slowly starts to sink and promotes the movement of air from the warm column to the cold column. Heat energy moves from areas where temperatures are warm to areas where temperatures are cold. High pressure aloft is associated with warm air aloft and low pressure at the surface. Low pressure aloft is associated with cold air aloft, okay, and high pressure at the surface. These differences in temperature produce differences in pressure. The difference in pressure over distance is called the pressure gradient force. And that's what gets the air down here on the surface of the earth moving in the first place. Right back to what Bud said. San Francisco blows, LA sucks, and we're in between. I'll be coming back to that from time to time. Now, how do we measure atmospheric pressure, and how do we show that on a surface weather map? The units of pressure in meteorology are called millibars. Now, since pressure falls as you go up, to Shaver Lake, pressure falls with increasing altitude. Weather stations at higher altitudes are always going to have a lower station pressure than places at lower altitudes, so it's not fair to compare them that way. So we adjust station pressure readings to sea level pressure to properly determine horizontal differences in pressure so we can figure out why the wind is blowing. All right, so here you go. Here's how this is done. Now, I'm not going to require you to look up a chart and see what the conversion factor is, but basically adjustments are made for station pressures to bring them to their sea level equivalents, and then all those things are depicted on surface weather maps. And the lines of equal pressure, the gray ones you see on the bottom, diagram C, are called isobars. Iso meaning equal, bar meaning pressure, so that we eventually get what's called a surface weather map that is drawn with current conditions on it. Now, figure 7.5a is a surface weather map showing every single observation of pressure being taken into account. Map B is smoothed out isobars, lines of equal pressure. So computers sort of smooth these out so they look nice and smooth when we want to have a very quick and dirty analysis of the surface pressure patterns across the United States, for instance, on a weather map. This map is an actual surface analysis from Saturday, January 5th, 2013 at 1 p.m. Pacific Standard Time. If you want to get a current map, you can click on that hyperlink and you can actually get the current weather map and then click on the full map to get a view just like this. Of course, it'll be a different day when you look at it from January 5th, but it will show you how a surface weather map actually looks compared to the rather homogenized ones in your textbook. Now let's go to upper air maps. How do we get upper air maps? Well, the data comes from those balloons we launched with the instrument packages on them that we talked about in a previous chapter called a radiosonde. But the maps for the upper atmosphere are drawn differently. Instead of showing pressure variations at a constant altitude, like at sea level, like we do at the surface map, the upper air maps show height variations along a surface of constant pressure. So it sort of shows you the same thing but differently. Those charts are called constant pressure charts or isobaric charts. And here's kind of the concept here. The lines on an isobaric chart are not called isobars, by the way. They call them contour lines. They connect areas of equal height above mean sea level in meters along a certain imaginary pressure surface. Now, you can't look up at the sky and say, oh, you see that line up there? That's the 500 millibar pressure surface. It's imaginary, but we get that information by launching those instrument packages from 69 places in the U.S. twice a day called radiosondes. What this means is, for instance, at the 500 millibar surface, which is what this chart depicts here, at the 500 millibar surface of pressure, that can occur at different altitudes depending on whether you're dealing with high pressure aloft or low pressure aloft. Obviously, you have a high height value. You're many, many thousands of meters above the Earth to find 500 millibars, then that's high pressure aloft. If you don't have to go up very far in comparison to find 500 millibars of pressure aloft, then that would be associated with low pressure aloft. The contour lines and the isobars in the northern hemisphere usually decrease in value from south to north because the air is typically warmer to the south and colder to the north. So typically you have high pressure aloft to the south and low pressure aloft to the north. That's especially true in winter. The elongated areas of high pressure in the upper atmosphere where the air is warm are called ridges, and the elongated areas of low pressure in the upper atmosphere where the air aloft is cold are called troughs. So in the upper atmosphere we deal with the undulating speed bump type pattern of ridges and troughs, ridges and troughs, ridges and troughs around the entire face of the Earth. Now here are two maps. 7.9a is the surface weather map that corresponds to 7.9b, which is the upper air map from the same day at the same time. So you can see low pressure at the surface and high pressure at the surface on the map on the left. You can see their relative association with low pressure aloft and high pressure aloft. So low and high on the surface and troughs and ridges in the upper atmosphere. The dashed lines on the map on the right indicate temperature contours in degrees Celsius. So obviously the colder the air gets near that purple low, you see minus 25 there. So cold air aloft is associated with low pressure, warm air aloft is associated with high pressure ridges. On a surface weather map, we use large blue H's indicating centers of high pressure. Those are called anticyclones. Large red L's indicate centers of low pressure, which are called cyclones. On a surface weather map, wind travels out of and around an anticyclone or a high clockwise in the northern hemisphere. Wind travels into and around a cyclone or low pressure system counterclockwise in the northern hemisphere. In the upper air maps, the winds blow parallel to the contour lines or height lines. All right, a little bit more about the laws of physics and why the wind blows. You learned a long time ago in science that an object in motion will remain in motion as long as no other force is exerted on the object. Second law of Newton's motions. The force exerted on an object equals its mass times the acceleration produced. F equals ma. Acceleration is either the speeding up or slowing down or change in direction of the object. It doesn't mean you're always putting your foot on the gas pedal. F refers to the net force that acts on the object, since there may be more than one force acting upon the object. What's the object here? Well, it's a moving blob of air, of course. Since air is an object that moves, these laws apply to it, these basic Newton's laws of motion. Now, with respect to WRT, that's what that means. It's a fancy abbreviation. You have to consider the following with respect to wind. You have to consider the pressure gradient force. We talked about that a little bit already. The Coriolis force, some say it's Coriolis effect. Your book says Coriolis force. Centripetal force, and the fourth one is friction. We'll explore the first two in the next few PowerPoint slides. First of all, the pressure gradient force. We explored it a little bit at the beginning of this PowerPoint. Simply the difference in atmospheric pressure at sea level over distance. On a surface weather map, closely spaced isobars indicate a strong pressure gradient. Widely spaced isobars mean a weak pressure gradient. Goes back to that whole thing that Bud said. San Francisco blows, LA sucks, and we're in between. Now the same goes for upper air maps with closely or widely spaced contour lines. Closely spaced contour lines means it's windy up there. Widely spaced contour lines means above your head, well, it's not so windy. If we looked at just pressure gradient force here, the force that causes the wind to blow in the first place, a difference in pressure between distance and the horizontal on the surface, it's always directed from higher pressure to lower pressure at right angles to the isobars. Air over high pressure moving toward area of low pressure to fill it in, basically. The closer the spacing of the isobars, the greater the pressure gradient. The greater the pressure gradient, the stronger the pressure gradient force, and the stronger the pressure gradient force, the greater the wind speed. So where those isobars are farther apart, like to the southeast of that high, you would expect lower wind speeds. To the northwest of that high in this graphic, you would expect higher wind speeds because the isobars are closely spaced. Now, I got to tell you that even though these red arrows do indicate the relative magnitude of the pressure gradient force, here's the deal. The air does not flow out of the high perpendicular to those isobars in reality. We'll explore why that is very shortly. Here is a surface weather map from your book. It's a very strong low pressure system with a central pressure of 972 millibars, with the pressure outside of it way up in North Dakota as high as 1,012 millibars, so that's really quite a strong pressure gradient force. And the line XX prime indicates the strongest pressure gradient force on this map. You also see the weather fronts depicted, and the little sticks have a legend on the right in blue that tell you how fast the wind is blowing at those places of observation.